Good evening, everyone. We will be starting in 5 minutes to let others join. Hello everyone. Welcome to the fourth live problem solving session for the course Fundamental of Semiconductor Devices, being taken by Professor Vijay Nath. So, a little bit about me. My name is Mayank Goel. I'm a research scholar at the Department of Electrical Engineering in IIT Bombay. About this course, so it the course Fundamental of Semiconductor Devices being taught by Professor Digvijay Nath, who is an associate professor at ISC Bangalore. For this week, we have looked at PN junctions. There's static behavior that is under equilibrium, and as well as their behavior under forward and reverse bias, current equations, current due to generation recombination, and an introduction to devices from PN junction. So this tutorial session is being conducted every Sunday 6 p.m. to 8 p.m. and the Google Meet link is this one which you have connected. So, like the previous sessions, I will be presenting you with some MCQ questions regarding this week's syllabus, and I hope that you all participate in answering these MCQ questions. So, first question. In a PN junction, which of the following best describes the movement of carriers immediately after formation? So just when PN and semiconductor join, what happens to the carriers? Holes diffuse from N side to P side, electrons diffuse from P side to N side, electrons diffuse from N side to P side, and holes diffuse from P side to N side. No carrier movement occurs. So what do you think should be the answer? You can speak or write in chat. So the answer to this will be C. Electrons diffuse from N side to P side and holes diffuse from P side to N side. So in the P side, there is an excess hole concentration, and in the N side, there is an excess electron concentration. So when they join, uh, there becomes a concentration gradient, and a diffusion of charge carriers occurs. So holes holes are moving from the excess P side to the N side, and electrons are moving from the excess N side to P side. And this diffusion is the reason there is a generation of an electric field. So a PN junction is in equilibrium. What does the built-in electric field do? Pushes holes from P side to N side, pushes electrons from N side to P side, opposes diffusion of carriers, enhances recombination everywhere. So what do you think is the answer? That is correct. The answer would be C, opposes diffusion of carriers. So the carriers are moving from P side, holes moving from P side to N side, and electrons from N side to P side. So this so when they go from the other side, there there builds an electric field in the at the junction point, which which is opposing this diffusion of carriers, and due to this, our depletion region is formed at the junction. So, next question: what is the depletion region in a PN junction? The region where excess carriers accumulate, the region containing only free carriers, the region depleted of mobile carriers due to recombination, the region where the Fermi level is constant. C would be the right answer. So depletion region is the region where the mobile carriers are depleted due to recombination. So when electrons are moving from n side to p side, they recombine with the holes. So the holes in the p side, since there is excess of holes in the p side, so they combine with the electrons. Similarly, the electrons are combining from when the holes are reaching from p side to n side, the electrons combine with and the excess electrons in the n side combine with these holes. So at the as soon as they are crossing the junction, they are getting removed due to recombination, and when the electric field is formed, no further diffusion happens. So at that region, there is you will find that there is no no free mobile carriers, and that is why it's called the depletion region. Which of the following statements is true about the depletion region? It contains no charge. It has ionized donors and acceptors. It has equal number of free electrons and holes. It forms only under external bias. So which of these is true about the depletion region? That would be correct. The correct answer would be it has immobile ionized donors and acceptors. So, so the doping that we have done is due creating these ionized donor has created these ionized donors and receptors. Since this so in a normal doped semiconductor, you have both the ionized donors and acceptors which are immobile, as well as you have electrons and holes, but which are mobile. But in the depletion region, the mobile carriers are depleted, so the only thing remaining are the immobile ionized donors and receptors. What is the built-in potential in context of a PN junction? The energy required to move electrons, the voltage that can be measured across the junction, the voltage difference due to the electric field created by the depletion region, the maximum voltage that can be applied to the junction. So which of these defines the built-in potential? That is correct. The answer is C. The voltage difference due to the electric field created by the depletion region. So the as we just talked about, the depletion region has created a built-in electric field, or you can say the electric field has created a depletion region. So that creates a potential difference between the p side and the n side, and this potential difference is called the built-in potential. Next question: the built-in potential of a PN junction depends on doping concentration, temperature, band gap energy, all of the above. That would be correct. The answer is all of the above. So the formula for built-in potential is given as kT by Q ln Na Nd by Ni square. So you can see it is depending on temperature here, as well as your intrinsic carrier concentration is also dependent on temperature. So there are multiple dependency on temperature. Your Na Nd are your doping concentration, and your Ni is also dependent on your band gap energy. So you know, the higher the band gap, lower will be your intrinsic carrier concentration. So this way your built-in potential is dependent on all of these parameters. If the doping concentration of the N side of a PN junction is increased, the depletion width increases on the N side, increases on the P side, decreases on the N side, remains unchanged. So the answer to this would be decreases on the N side. So the charge neutrality equation in the PN junction becomes NaWp equals to NdWn, where Wp and Wn are the depletion widths on the P side and the N side, and so and Na and Nd are the doping concentration on the P side and the N side respectively. So you can see, as you as you are increasing the doping concentration on the N side, your depletion width on the N side has to decrease. They are inversely proportional. If the doping concentration on the P side is significantly higher than on the N side, what can be inferred about the depletion region? It will be wider on the P side, it will be wider on the N side. The depletion region will be negligible on the P side, the depletion region will be negligible on the N, will be same on both sides. Yes, the answer to this would be the depletion region will be negligible on the P side. So, so you you just saw the formula. So, if your Na is very much greater than your Nd, like several orders of magnitude, then your depletion width also in the N side, depletion width on the P side will be several orders of magnitude lesser than the depletion width on N side. So you can so you can ignore the depletion region in the P side compared to the N side. Now it's a numerical question. Given a silicon PN junction with Na is 10 per 16 per centimeter cube, Nd is 10 per 17 per centimeter cube, and Ni is 1.5 into 10 per 10 per centimeter cube, and the temperature given is 300 Kelvin. You have to calculate the built-in potential, built-in voltage. You can take kT by Q as 0.026, because that is the value at 300 K. The options are 0.51 volts, 0.65 volts, 0.76 volts, 1.2 volts. I will give you some time to solve this. So I hope some of you have tried this question, tried this question. So the answer to this question would be 0.76 volts. So we just saw the formula for built-in potential. So KT by Q, you take it as 0.026. Na, you are given 10 raised by 16. Nd, you are given 10 raised by 17. Ni, you are given 1.5 into 10 raised by 10. You put this all values here. You take the log. You multiply with this. You will get the answer 0.76 volts. Next question. The depletion width in a PN junction is given by W equals to 2 epsilon VBI by Q. W equals to under root 2 epsilon S VBI Na plus Nd by Q Na Nd. W equals to epsilon S Q Na plus Nd. W equals to Q VBI by 2 epsilon S. So the answer to this would be B. I guess the other ones don't look as complicated. So it's easy to recognize this. So so you can see the depletion width is dependent on your built-in voltage as well as your doping concentration. Epsilon S is your dielectric constant of the semiconductor. So you also just saw the formula, the N NAWP equals to NDWN. So and you know that depletion width is sum of WP and WN. So by merging the two formulas, you can get the formula for WP and WN as well in terms of VBI, NA, and ND. Next question. When a PN junction is forward biased, what happens to the depletion region? It widens, it remains unchanged, it narrows, it disappears completely. That is correct. The correct answer would be it narrows. So when the PN junction, when you forward bias it, there will be more injection of charge carriers in the N side and P side. There will be more injection of electrons in the N side, more injection of holes in the P side. So that will create a that will create more recombination at the that will create a higher recombination, and it reduces the depletion width. If a PN junction is reverse biased, what happens to the depletion width? So earlier we saw what happened when it was forward bias. Now we talk about when it is reverse bias. Increases, decreases, remains the same, decreases, then increases. That is correct. The answer would be it increases. So when you reverse bias, so what it is doing, it is taking electrons away from the p side, and it is taking holes away from the n side. So where it was all there were already minorities. So what happens is they will try to So the holes that are coming from the p side to the n side, they will come even further into the n side, and similarly electrons will go further into the p side, so that will increase the depletion width. Next is another numerical. If the depletion width of a PN junction is 500 nanometer and the applied built-in potential is zero point 0.7 volts, what is the approximate electric field in the depletion region? 1.4 into 10 to the power 4 volt per centimeter, 2 into 10 to the power 4 volt per centimeter, 1 into 10 to the power 5 volt per centimeter, 3.5 into 10 to the power 5 volt per centimeter. I will give you some time to solve this question. So anyone got the answer for this question? It's very simple. So the answer to this will be 1.4 into 10 to the power volt per centimeter. So electric field is nothing, just built-in potential divided by the depletion width. So you divide zero point 0.7 by 500 nanometer, and the answer you get is 1.4 into 10 to the 4 volt per centimeter. Next question. If the total depletion width is 400 nanometer, what is the depletion width on the N side if Na is 10 to the power 17 and Nd is 10 to the power 16 per centimeter cube? A 40 nanometer, B 100 nanometer, C 300 nanometer, D 360 nanometer. This is another numerical. So we just saw the formulas for depletion width in Na and D. Anyone with the answer? So the answer to this will be 360 nanometer. So we know that NaWp equals to NdWn, and we also know that Wp plus Wn equals to W. So by substituting, we can get Wn equals to W into Na upon Na plus Nd. So W we know 400, and Na is 10 raised to the power 17, Nd is 10 raised to the power 16. You put them here, this will come out to be 1 divided by 1.1. So 400 divided by 1.1, which is approximately 360 nanometer. So next question. The capacitance of a PN junction is in equilibrium is given by C equals to Q Na upon epsilon SW, C equals to epsilon S by W, C equals to epsilon S Q divided by Q NaW, C equals to epsilon S by VBI. So what is the formula for capacitance? So the answer to this is C equals to epsilon S by W. So again, epsilon S is your dielectric constant of semiconductor, W is your depletion width, and C here is not capacitance, it's capacitance per unit area. So it's basically capacitance density. Generally in semiconductors, we always talk in terms of per unit area because because if you see we only take into consideration the length of the semiconductor. We don't take into consideration the width and the height, the thickness of the semiconductor. So we consider everything in terms of per unit area. So many times you won't see it written as C equals to epsilon S. So here the C by C you are meaning capacitance per unit area. So the capacitance in a capacitance terms would be epsilon S A divided by W. What is a quasi Fermi level? The level where equilibrium is maintained, a local Fermi level indicating carrier concentration, the maximum energy level in the junction, a theoretical concept with no real application. That is correct. The Fermi level is quasi Fermi level is a local Fermi level indicating carrier concentration. So you can see a PN junction is basically made up of two semiconductors, a p doped and an n doped. So each of them will have their own carrier concentration. So each of them have has can have its own Fermi level. So the so that is why it's called a quasi Fermi level. So not it's not a true Fermi level, but we can consider it as the Fermi level to indicate the carrier concentration. The quasi Fermi levels in a forward bias PN junction remain the same, split apart, merge together, disappear. So the correct answer would be split apart. So in equilibrium, we consider the Fermi levels to be constant. So in equilibrium, they are they are joint. The Fermi level for the p side and the n side is joined and is at the same energy level, and the your conduction and valence band bend accordingly. Their positions are according to the quasi Fermi levels. So when you forward bias the p-n junction, there is a positive potential at one end and the negative potential at the other end, so which causes the Fermi level to separate and go go down or up accordingly. Like in it will go up in a p type and it will go down in a n type. Uh, uh, it will go down in a p type and up in an n type. So they break apart. The ideal diode equation is given by I equals to I naught e power qv by kt. I equals to I naught e power qv by kt minus 1. I equals to I naught e power minus qv by kt. I equals to I naught e power minus qv by kt minus 1. Yes, the correct answer would be I equals to I naught e power qv by kt minus 1. So also, so just I talked about capacitance. Here also many places you will find it instead of I, J is written. So J is basically current density, current per unit area. So since like just I said that we many times we talk in terms of per unit area because we are not taking consideration the width and thickness of the semiconductor. So this formula basically your I naught is your minority carrier concentration and E power QE by KT is the excess carriers injected due to the potential applied potential. So here the V is the applied potential. In reverse bias, why does the current remain very small? Majority carriers flow easily, no carrier supply at the depletion edge, built-in potential disappears, the P side becomes N type. Yes, the answer would be no carrier supply at the depletion edge. So, so as you talked earlier, when we reverse bias a junction, so the minority carriers at each end are going out. So, so there is no way of getting majority carriers from the other end. Hence, there is no carriers getting through the PN, getting through the depletion region. Hence, there is no the current is not able to flow properly. The diode equation I equals to I naught e power qv by kt minus 1 holds only when the diode is reverse biased, the diode is forward biased, the diode is unbiased, the diode is in breakdown. So the answer to this would be the diode is forward biased. So, so when we just saw that, so this 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 formula E par QE by KT assumes that majority carriers are being injected into the semiconductor, and that only happens when the diode is in forward bias. So when the diode is in reverse bias, there is no carrier injection in the semiconductor. Hence, this formula is not valid. Next question. If the diffusion length of electrons in a p-type region is Ln, what does it represent? The average distance electrons travel before recombination, the width of the depletion region, the length of the diode, the region with zero carriers. So which of these tells us about the diffusion length of electrons? Yes, the answer would be A, the average length distance electrons travel before recombination. So basically, in a p-type region, the majority carrier concentration is holes. So when you inject an electron from one end, it gets recombined with one of the holes, but there is a length it can travel before there is an average length it travels before it gets recombined. That average length is called Ln. So this this diffusion length represents what is your size of the diode. So if your length of the diode is much greater than the diffusion length, your diode is called a long channel diode, a long diode. If your length channel if your diode length is comparable or less than your diffusion length, it is called a short diode. Basically, in a short diode, all the carriers that are being injected are are going on the other side without any recombination. The diode ideal factor n in real diodes is exactly 1, between 1 and 2, always 2, greater than 2. What is the ideality factor in real diodes? So the correct answer for this would be between 1 and 2. So in an ideal diode, the ideality factor is 1. But if we are talking about real life diodes. In real life diodes, the ideality factor is increase is changed, and it falls between 1 and 2. It generally falls between 1 and 2. What is the key assumption in the derivation of the diode equation? A. Quasi Fermi levels remain constant. B. Recombination in the depletion region is negligible. C. Majority carrier diffusion dominates. D. The depletion region remains neutral. So the answer to this would be recombination in the depletion region is negligible. So we are so when we so if you see the formula, it is I naught e power qv by kt minus 1. So there e power qv by kt is the amount of carriers being injected due to the applied potential, and I naught is the minority carrier current. So we only assume that we have that that there is only recombination in the channel region, which is corresponding to the minority carrier current, and there is no there is no recombination happening in the depletion region. So all the injected excess carriers are going to the other region, going are crossing the depletion region. So that is how we get the ideal diode equation. The diode's turn on voltage is approximately equal to the built-in potential, B, the intrinsic carrier concentration, C, the depletion width, D, the breakdown voltage. So this is a very simple question. Anyone with the answer? Okay, the answer is here itself. Sorry for the confusion. The answer is the built-in potential. So, so when you apply a voltage that is approximate, so when you are applying the, so the effective potential is given as VBI minus V, where VBI minus VA. VA is your applied potential. So when you are up, so when you apply your a potential that is almost equal to your built-in potential, your depletion width, you can consider that your depletion width disappears. So since there is no depletion width, you will get an all your carriers that you are being injecting, it is going directly to your is going directly to the other end and contributing to the current. And since the carrier injection is exponential, you will see an exponential rise in your current. So this point is called turn on voltage, and hence the turn on voltage is almost equal to your built-in potential. Can anyone tell me what is breakdown voltage? Have you read the term breakdown voltage? So 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 as you as we have so when you are applying a reverse bias to your potential diode, so we just read that the your depletion width is increasing in the diode. So as you apply more and more your voltage, your depletion width will increase more and more. So at a certain point, your depletion width will become equal to your length of the diode, and your then your depletion width becomes your diode. There is no p channel and n channel left. Your depletion width is your diode, so it basically becomes a single channel where all the current is flowing, and you will see a sharp, you can see, so when you had the depletion region you had almost negligible current, but as soon as it reaches that potential, you will see all your applied voltage, it goes directly into current generation, and you will see a sharp increase in your current, and this point is called your breakdown voltage. And in most normal diodes, this is a permanent breakdown. So you cannot so even after removal of your diode, removal of your potential, it does not, your diode characteristics do not recover. They will they will still give continuous high current. If the ideality factor n of a diode is close to 2, it suggests that the diode is ideal. Diffusion dominates the transport mechanism. Generation recombination dominates the current. The diode is in breakdown. So what does ideality factor 2 means? So the answer to this would be generation recombination dominates the current. So due to presence of traps in your depletion region, you have generation recombination happening there. So when your minority when so this due to this there is regeneration recombination happening in the depletion region, and this is resulting in a current. This is what, and when and this is non-ideal case, and at this point your identity factor is close to 2, which means your current will be I naught e power qv by 2 kt minus 1. So you can see it's almost it's high, it's almost e square root of the current is almost square root of what it should be. In a diode, when does generation recombination current dominate over diffusion current? At very high forward bias, at very low forward bias, at breakdown voltage, when the diode is in open circuit. So the answer to this would be at very low forward bias. So you see, when we have forward bias, you are injecting majority carriers from your from outside, which are diffusing over the depletion region. So at high forward bias, you will have much higher carriers injected, so your diffusion current will be very high. So at low forward bias, your diffusion current is low and your generation recombination current is higher. So which which is why you see a very low current in at low forward bias, and once you overcome the depletion region, then you see an exponential rise in current. The generation recombination current in a PN junction is due to only minority carriers, traps and defects in the depletion region, tunneling effects, direct recombination only. So I had just answered this question few minutes back. The correct answer is actually B. The generation recombination current in the PN junction is due to traps and defects in the depletion region. So in the depletion, the traps and defects, they act as recombination sites. Hence, when there are traps and defects, you have a recombination current happening happening inside the depletion region. which which so when you have recombination in the depletion region, so your excess carriers are not going completely towards the other end, so that reduces your diffusion current. Hence you will you have a low amount of current when there is generation recombination happening in the depletion region. What characteristic allows a PN junction diode to behave as a rectifier? It allows current to flow in both directions. It allows current to flow in one direction only. It increases resistance in both directions. It has no effect on current flow. That is correct. So you see, in a PN junction, when we are reverse bias, we have very less current. But when we are forward bias, after the turn on voltage, we have an exponential rise in current. So we have very high current. So we can say that when the PN junction is forward bias, it conducts current, and when it is in reverse bias, it does not. It acts as an insulator and does not conduct current. So this property allows it to act as a rectifier. So now, what is a rectifier? So a rectifier is a device. So we will study this in the next class, but I will tell you, a rectifier is a device that allows you to convert your AC current to DC current. So, so you see, in AC current, you have your current is going between forward and negative, positive and negative. So if you add a PN diode in between, it will only allow your positive current to go through, and it will block the negative current. So that way you will have only po- uh, at the output you will only have positive current and you won't have negative current. So this is one way to convert your AC current to your DC current. So let's end with a good numerical. A silicon diode has a reverse saturation current of 5 into 10 to the minus 12 amperes at 300 Kelvin. If a forward bias of 0.5 volts is applied, what is the forward current? You can assume Kt by Q as 0.026 volts. Options are 0.1 milliampere, 0.53 milliampere, 1.02 milliampere, 5.3 milliamperes. Anyone able to anyone able to solve this question? So the answer to this would be 1.02 milliamperes. So you know the formula is I equals to I naught E power QV by KT. So V you can also write as a V by QT by Q, and QT by Q you know 0.026. V you have been given as zero point 0.5 volts. So you calculate this E power zero point 0.5 by 0.026, which comes approximately 2 into 10 raised to power 8, and this is, and then you have to subtract 1, but it is greater than 1, so remove you can approximately remove the 1, and then you multiply it with your saturation current, which is 5 into 10 to the power minus 12, and when you multiply it you get 1.02 milliamperes. So these are the type of questions you can ask in about a PN junction. So these are the questions I had for today. Thank you for attending this session. If you have any doubts, you can ask. You are welcome, and feel free to ask any doubts if you have regarding this week's or any previous week's course subjects, topics.